Today we are talking about seismic waves. And I start with the question, why is there damage to places that are not directly on the fault? Well, it's because seismic waves carry the energy from an earthquake away from the focus through the Earth's interior and across the surface. We saw that with the picture that we drew earlier. And the picture looked, if I can kind of remind you what we drew something like this. I think it was a normal fault, like this. And we had the focus down here, the epicenter directly above, and then we had our seismic waves coming from here. And we said that the first place they hit is the epicenter here. Okay, it might not, the fault line might be at the epicenter, but it might not be in a case like this. So why are places here destroyed, but also places a little bit further away? And the reason is because that energy is carried by these seismic waves. And there's going to be two types of seismic waves. There's going to be waves that travel underground, like you see here in this little version. And then once those waves reach the surface, they're going to create waves along the surface. Those are surface waves. So we have surface waves here, which we'll talk about second. And then we have our body waves down here, which is what we're going to start with as we talk about seismic waves. So the seismic waves are carrying the energy from the focus out to everywhere else. There are two main categories of seismic waves, body waves and surface waves. Then each of those have two more subtypes. So really we're going to be talking about four types of waves in this section. We're starting with the body waves. Body waves are waves that travel from the focus through the body of the Earth. Okay, they're underground. Simple terms, body waves start from the focus and they travel underground. There are two types, as I said. The first ones are the P waves. The P stands for primary. Think of the word primary. Primary means first. These are the first waves to arrive at a location. Why are they the first waves? Because they're the fastest. How fast are they? Really fast. You see in the crust, they're about 4 to 7 kilometers per second. In the mantle, 8 to 8.5 kilometers per second. In the core, they're even faster. I don't have the number for that here. Why are they so much faster in the mantle and the crust? The mantle is more dense. And we're going to see that the density is going to matter with these primary waves. Primary waves are compressional. So they travel by contraction and expansion. I'm going to demonstrate this with a slinky in class tomorrow, so you'll be able to see what I mean by this. The particle movement is going to be parallel to the direction of wave motion. So I'm going to tie a little string on the slinky that I used to demonstrate. And you're going to see that as I compress the slinky coils, the wave energy is going to go back and forth like this arrow. Okay? And then the particle movement is also going to go back and forth. So the particle motion is going to be in the same direction with this contraction and expansion with the wave energy. We said, why do they go faster in the mantle? Because it's more dense. Imagine this is rock. Okay, it's not a slinky anymore, it's rock. And you're going to have one piece of rock hitting the next piece of rock, which hits the next piece of rock, which hits the next piece of rock. The denser the rock is, so the denser the molecules of the rock are, the faster that wave is going to propagate through it. Will it work in solids? If I hit a solid, will it transfer to the next molecule, the next one, the next one? Sure. Will it work in a liquid? Can I hit the molecule of a liquid, which will hit the next molecule? Sure. So this will happen in liquids too. This type of wave actually travels in gases too. Sound waves are a good example of compressional waves. When I speak, the sound waves are going through the air, compressing the air. They go to your eardrum, and your eardrum bounces in and out with those compressions, and you can hear me. So compressional waves will travel through anything. For us, when we're talking about earthquakes, solids and liquids are the key things. The earthquake waves will travel through solids and liquids. And I'll show you a little video and show you an animation to show you this. And we'll do it in class too. S waves, what do you think the S stands for? Well, secondary. It's not primary anymore, it's secondary. Why are they second? Because they're slower. The speeds, you don't have to worry about writing down the speeds. Just realize that they're about half the time. Okay, you're about half the speed. Secondary waves are transverse waves or shear waves. What that means is the particle movement is perpendicular to the direction the wave travels. So again, imagine if I have a slinky or a rope in this case, and we'll demonstrate with a slinky, that the wave energy is going to be going back and forth this way. So the wave energy will be going back and forth that way. But the particle motion is going to be vertical, up and down in this case. And again, realize in the Earth it could be side to side, whatever. The key is perpendicular. It doesn't have to be up and down. Think of it in 3 dimensions. It's just going to be perpendicular to the direction the wave propagation is. S waves will not travel through liquids. Okay, this works in solids. Or if I take one particle or molecule of solid and I raise it up really quickly, the next one's going to go with it, and the next one with it, and the next one with it. Okay, so it works for solids. It does not work for liquids or gases. So these waves will not travel through liquids and gases. Let's look at some animations of these. Here's the first one. This is going to be a P wave. There you see the compressional idea. And you see the blue dot there is a particle of earth, dirt, rock, whatever. So you see it's going to go parallel to the direction of the wave motion. This animation is for an S wave. You see that the particle is perpendicular to the wave motion. Again, in this case, it's vertical. Don't get into the habit of thinking that it's vertical up and down. Just think of it as perpendicular to the way the wave is traveling. The reason why I have these back to back is so you can see the speed. So I'm going to start this one and let it go through once. Maybe let it go. There we go. And then I'm going to start this one when that one ended so you can see the speed. That P wave is about twice as fast. So I'll do that again. I'll start this one, then get this one ready. Start there. So they start together, and you see the P wave is about twice as fast as the S wave. And here's the animation with the slinky, so it's kind of to reinforce what it is. Here's another science teacher that is going to explain it with a slinky.
What I'm going to represent is an earthquake. So I'm standing on the surface of the earth, and in class we talked about the whole idea that there's this idea of the fault. So we can assume that the fault is relatively shallow compared to the length of the earth. And so even though I'm not going to have the fault starting down here, the earthquake is going to start on the surface of the earth and it's going to travel through the substance. Okay, so here's how this works. So P waves, who can remind me what's important about P waves? What did we just learn? 2 things.
They're fast.
They're fast, and number 2,
They go through solids and
they go through solids and liquids. So this, and P waves, and the other thing that we're going to add to those notes that we took in class is that they bump into the thing next to them. So this is how it travels. So here's a P wave. I'm going to simulate an earthquake by pushing the ground. And this is how a P wave travels. It bumps into the thing next to it. Watch it one more time. Just look at the rings of the slinky. What happens to the rings of the slinky as I have the earthquake? I know you're about to raise your hand.
yeah, they're like together.
Bingo. They get closer together. Everybody see that? Okay, watch this one more time. Watch how the rings get closer together. Okay, so they bunch, and then that bunch of coils just kind of moves. That bunching kind of moves all the way down. And if it hits something else, it bounces back. Now S waves are a little different. They move in a side-to-side motion. So to model how an S wave travels with the slinky, what I'm actually going to do is just take the earthquake and it's going to model a side-to-side motion. Now watch how the slinky moves. And here it is. Okay, so you guys see how it kind of moves side to side? So it's very different. Now if there's a bit more energy to it, it'll bounce back as well. Okay? Okay. So, do you think this slinky is modeling solids, liquids, or both? Dylan, what do you think? Solids, liquids, both? Solids. Okay, good. It's solid. So this is measuring solids. Okay? So, because S waves don't travel through liquids, right? So all models work to a certain extent. At some point, the model doesn't work exactly like it's supposed to. And that happens with every.
So we'll stop it there. And we'll do the similar thing, like I said. So if you are in class, we're going to do a demonstration with the Slinky as well. We just won't be able to do the slow motion. I won't have the cool animations or anything um, on it like that. Look at this little chart here. It's kind of a neat one. Take a look at it. What is it showing you? Anyone? The red are the P waves. Blue are the S waves. This is depth into the Earth, going from the surface to the inner core. On this side is speed. So what you see is the P waves are starting to travel faster, so are the S waves, in the mantle. But then look at the S waves stop at the outer core. Why do the S waves stop when they get to the outer core? Because S waves cannot travel through liquids. Okay, so S waves cannot travel through liquids. That's why you see them stopping in the outer core. Then the last animation I want to show you for this, and we're going to actually look at this again when we get to seismographs, but I think it's important to look at it now too, to show you again this P waves and S waves, because we're going to start looking at seismograms to identify the P waves and S waves. So seismogram is just an instrument that measures and records earthquakes. Like I said, we'll talk about them, we'll take notes on them later. Basically, you have a piece of paper on a spinning drum, and you get it spinning, you have a marker on top with the weight, the earthquake shakes. You'll notice, and I'll play it again for you in a second, but you'll notice that the weight has a lot of inertia, so it's going to keep the pen steady, and it's going to be the paper that moves. So you'll see that in the next time. So the pen is steady, the paper moves underneath it, and it's going to draw the waves onto it. Like I said, we're going to see this again when we talk about the seismographs and seismograms. But what you notice is when those earthquake waves hit is with the seismic waves. You see them right here. P waves are the first one to arrive because they're fastest. S waves are the second to arrive because they're slower. And then we're going to get to the surface waves next. But the surface waves are the slowest. They're always after the S waves even. So we're going to be seeing that next. So now we're on to the surface waves. So we had our body waves. We did those. Remember P waves and S waves. Now we're on to our surface waves. Surface waves are just waves that travel from the epicenter across the surface of the Earth. They are created by the body waves once they reach the surface. So there's kind of four things about them. They're always going to arrive after the body waves because they're created from them. They're going to travel slower than the body waves. They're going to die out faster than the body waves, so that means they travel less distance. But they're going to be more damaging than the body waves. And I'm going to show you that with some animations of how these waves move. Buildings do not like the motion that these waves show. So there are two types. Those two types are Rayleigh waves and love waves. So let's look at them and see some animations. In Rayleigh waves, the particles move elliptically, like ripples in a pond. And you see this little picture here showing that if you want to draw a little picture next to your blank there, you can. Think of it like the Earth going like this, so it's actually rolling, and it has this little circular backwards motion. Buildings do not like this circular backwards motion. And we can look at the animation again and to reinforce this, why they don't like it.
As Rayleigh waves travel in backward rotating circles, they cause the ground to accelerate through a vertical lift, a horizontal push, a vertical drop, and a horizontal push in the opposite direction.
We can show that again, and as you see it again, it's that backwards motion. Buildings do not like that backwards motion. It's going to go up, back, down, forward.
A vertical lift, a horizontal push, a vertical drop, and a horizontal push in the opposite direction.
Okay, so buildings don't like that kind of motion. These are very bad for buildings. Second type are love waves. In the love waves, the particles move back and forth horizontally in a zigzag motion. So you see in this picture, if you wanted to draw a picture, I guess you could. Not too much to draw like a top view. And kind of what you'd see is the ground moving back and forth, kind of in a zigzag motion. Kind of, going back here, these Rayleigh waves, does the ground actually roll like this? It can. Like you saw in that little animation, the ground can actually roll. It's going to need to be a big earthquake and usually fairly loose soil, but sometimes you can actually see these rolls of the ground, coming at you, maybe if you're unlucky. So love waves, the ground is going horizontally. Again, buildings do not like that. Imagine if you had a building standing here. That's a pretty bad drawing of a building. But you have a building standing here, and all of a sudden, the base of the building gets ripped out from underneath it. Buildings do not like this. Here's our animation. So we see this just side-to-side motion. And again, if a building was on there, a building is not going to like that motion. So those are the 4 types of waves. Again, we had our body waves, the P&S waves, and then we had our surface waves, the Rayleigh waves and love waves. Now we're going to talk about a couple other things with our earthquake waves. I'm not going to spend too much time on them now, but I'll tell you a little bit of the stories with them and I'll demonstrate more. We're going to talk about earthquake resonance and building height. And I'm going to demonstrate this with a little model that I can strap onto the earthquake machine. And basically it just shows you that the height of the building matters during an earthquake, because an earthquake can vibrate at just the right speed to amplify the waves. And I'll show you this video. We're not gonna have time to watch the whole thing now, about the Galloping Gertie. And basically it was the Tacoma Narrows Bridge, and the wind was blowing just right and the building was engineered very poorly. And because the wind was blowing at just the right speed, it got the bridge to be in resonance, and the waves amplified and caused the bridge to do this. Like I said, we can watch this video in class, or if you really want to watch it, I put a link in my playlist. You can watch the kind of the end result or the final result of this bridge. But this is this idea of resonance. And buildings can be in resonance similar to this during an earthquake. And certain heights of buildings can be more susceptible. Like I said, we'll do a demonstration of that in class. Last thing I wanted to talk about with waves is this idea of the conservation of energy. We talked about conservation of momentum in our physics unit, and this is similar. So this is the total energy at the end of any event is equal to the energy at the beginning of the event. And again, some is going to be lost because of friction and stuff like that, but the idea is the energy at the end is going to be the same as the energy at the beginning. And there are a couple really good examples of this happening. And Mexico City 1985 is a good example, and I can tell a quick story about that. And then Loma Prieta in 1989, that's the big San Francisco earthquake, is another good example of that. Basically, the idea is that earthquake waves going through dense solid rock go really, really quickly. We can show that or see that in this animation.
The fact is that seismic waves are modified, actually distorted, by the rocks they pass through. When seismic waves pass from harder into softer rocks, they slow down. This slowing means they must increase their amplitude to transport the same amount of energy. During earthquakes, the shaking tends to be stronger where seismic waves move slower, but with greater amplitude.
So if I play that again, let me take out the sound. So we see in solid rock, the waves are going really fast, but the amplitude is really small. Once it gets to softer ground or looser ground, it has to amplify because the energy at the beginning of the event has to be the same as the energy after. So the waves amplify, there's more shaking. So do you want to build your house on solid rock or on loose ground? I think there's a Bible story about that. You want to build on the solid rock. The waves are going to go through quickly with not as much amplification. Well, that's what happened in the Marina District in San Francisco. So kind of quick history lesson, very, very quick. So San Francisco, booming city, 1906, huge earthquake. Destroyed most of the whole city. 90% of the city was destroyed, huge fire, burned all wood buildings. The other buildings made of brick were destroyed. Whole city in ruin. What are you going to do with all this garbage from the previous earthquake? Well, they had the idea of let's kind of put it into the bay. They had to get rid of it. They pushed it into the bay, and it made a big pile of rubbish in the bay. And that was 1906. So you get to the 1910s, 1920s, everybody knows that this is essentially rubbish, garbage. But then it starts getting covered up by grass and stuff. So we get to 1940s, 1950s, and people stop realizing that this was just garbage from the 1906 earthquake. Get to the 1970s, there's grass growing on it. It's a really kind of neat place. And 1980s, they start building some condos and some really nice buildings on it. And it's called the Marina District because it's right on the water. And then, of course, in 1989, there's a huge earthquake. And if I kind of draw a little bit of a picture, we had Candlestick Park is where the World Series was happening in 1989. You might have heard. So at Candlestick Park, the builders were smart. They made Candlestick Park on an outcropping of rock. And kind of surrounding it is the Marina District. So this kind of looser, I'll just put some dots here, this really loose soil, kind of landfill from the 1906 earthquake. So they're starting the warm-ups for the World Series. Rafael Palmeiro is rounding the bases. Al Michaels on the TV broadcast. They're introducing the World Series, and there is this huge earthquake. The earthquake starts shaking the ground. The waves are really, really small and fast through the solid granite here. It gets to the Marina District where it's loose landfill essentially, and the waves slow down, and when they slow down, they have to amplify. So they get bigger because they slow down. And it destroys pretty much all the buildings in the Marina District. You see pictures of buildings like this. This is the second floor. There's a balcony on the second floor. The first floor is pretty much gone. Okay? So people in Candlestick Park, they felt the earthquake, but it wasn't that bad. They didn't think it was that bad. They went outside the Marina District and they saw everything was destroyed. They were built on solid ground. The waves went through quickly with low amplitude. When the waves had to slow down because it was less dense soil, they amplified. A lot of people in the Marina District, in their yards, they found these old bricks had surfaced through the dirt. It was the garbage from the 1906 earthquake. Mexico City earthquake in 1985, similar case. The earthquake, 1989 or 1985, was actually down here in the Michoacan Gap, a long way from Mexico City. But Mexico City was the place that was destroyed by the earthquake because of this idea of conservation of energy. If you know a little bit about the history of Mexico City, and I don't know much, but I know that basically it used to be a capital city of the native people that were there. And Tenochtitlan, I think, or how you pronounce it, that was their city. And their city was a greatly defensible city because it was surrounded by a swamp. So there's kind of water here. Very defensible city. Well, the Spaniards came and defensive city, but they still were able to overtake it. And they built their capital city of Mexico City on top of it. Mexico City grew and expanded. They ended up filling in this marsh and building Mexico City on top of it. Okay, so that's all kind of in here. Earthquake happens over here, Michoacan Gap. The waves go through the mountains very quickly, low amplitude. They get to this filled in marsh where it's loose soil. The waves amplify. So amplified waves there, and in the center they're small, amplified waves, and it destroyed Mexico City. A horrible earthquake. But again, it's this idea of conservation of energy. That the more dense the ground is, the waves can go through quickly. without much amplitude, but if it's really loose soil, the waves will slow down, which will cause them to amplify and cause much bigger destruction. That's it for seismic waves.